Good morning and welcome to Math in the Morning. Thanks for being here, you guys. I had to work kind of hard today to get this going. So I can't wait to share with you these slides about forcing to softly kill degrees of inaccessible. And you get an idea for how these kind of proofs go. But the one that we're going to be doing for the measurable case and for the supercompact case is going to be kind of a lot different because you're lifting these embeddings. So with the inaccessible cardinals, we don't have the embeddings part. So so go ahead and pull up the first slide. Okay, I was gonna tell you guys some like tea in the town, but okay. So this morning I was like, usually it's like very, very quiet here, but this morning it was like, they were like yelling in the street, and someone was like, don't go on my Facebook page. Nobody goes on my Facebook page. There's like some drama in the streets and I keep thinking about it. And then my cat Evie was like, wait a minute. I don't want anybody going on my Facebook page either. And I was like, oh boy, I don't even know if she has a Facebook page. Okay. So anyway, that was the drama day. We just heard some people fighting outside about someone going on someone's Facebook page. Anyway, I don't know why I had to share that. Okay. So anyway, step one. Let's get into it. This is a little bit drama too. So maybe that's why there's sort of some drama going on here in this in these theorems. Okay, so the theorem is if kappa is alpha inaccessible, then there's a forcing extension where kappa is still alpha inaccessible but not alpha plus 1 inaccessible. Okay, and you could start off and say if kappa is not alpha plus 1 inaccessible, then just force trivially. And you're in a universe where it was what you wanted. So what do we want? We want to be in a universe. In the end, we want to be in a universe where kappa is alpha inaccessible, but it's not alpha plus 1 inaccessible. Okay, and we're going to do forcing that Cohen invented. And I also think yesterday I was like, oh, maybe they did the club forcing right when model cardinals were invented. But I think like that doesn't make sense because like model cardinals, I don't know when they were invented, but it was before the 1960s, and then in the 60s that's when Cohen invented forcing. So it's this technique, amazing, won the Fields Medal technique where you can go from a model of ZFC to another model of ZFC where something's slightly different. And he did it for changing the size of the continuum, the size of the real numbers, by adding new binary sequences. You can add a new binary sequences, aren't they already here? I know, it's amazing. Okay, so anyway, we're gonna have some forcing characters in this. Okay, so the first step when we're doing this forcing, I'm getting excited, you guys. The first step is to force the generalized continuum hypothesis if needed. This preserves all, it does not create or destroy any inaccessible cardinals. And so we don't change anything about the inaccessibility of kappa, but we sort of make the GCH pattern look nice. So the power set of aleph 1 is aleph 2. The power set of aleph naught is aleph 1. So the real numbers are size aleph 1. Everything is maybe as it should be. I don't know. Everything's nice. So we can do some math here. It's sort of like we're working in this world of independence where you can have a lot of things different. So, but if you want to do some math, sort of know where things line up, then it's nice to have the GCH. And we can always force it without like destroying the inaccessibility or anything like that. Okay, so G subset of P is V generic. So we go to that universe. Okay. Step 2, add a club to kappa which contains no alpha inaccessibles. Okay, so we have this club, and this club says, and they're sort of like, they're forcing, but I wouldn't be too scared of these guys because they preserve a lot. They do something, but they're tough guys, but they're quite gentle because they preserve a lot too. Okay, I preserve cardinals and cofinalities and strong limits. I add a club. It should say I add a club with no alpha inaccessibles, but I have unboundedly many beta inaccessible cardinals for beta less than alpha. Okay, and I'm like abbreviating, calling them inaccessible cardinals. So in this new universe, so H subset of C is V of G generic. So in V of G of H, kappa is still alpha plus 1 inaccessible. You have this nice continuum pattern, and now you have this club. So far it's not doing really anything, but it is a club. Does not have any alpha inaccessibles. Okay, we know that if kappa is alpha plus 1 inaccessible, it's a limit of alpha inaccessible. So there's something going on there, because if kappa were to remain alpha plus 1 inaccessible in the final extension, it's a limit of alpha inaccessible. So let's see what's going to happen with this C. Okay, so step 3. Okay, so now we're forcing with E. And E is for Easton's forcing. So Easton showed that like you can make the continuum, assuming some basic rules, you can make the continuum patterns be sort of whatever you like. And so, in this particular, we're going to use Easton's forcing to change the continuum function. So what we're going to do is force 2 to the gamma plus to be delta plus, where a gamma is in C and delta is the next element of C past gamma plus. Okay, so we have this club, and then we're changing the continuum pattern. So what does E do? So E preserves all cardinals and cofinalities, but E says I destroy all strong limits that are not limit points of C. Okay, I want to see if I can explain this really quickly on why it destroys all limit points, strong limits that are not limit points of C. So suppose we had some lambda that was a strong limit below kappa, but it's not in C. So that means there's some element delta in C, like below lambda. I hope I can say that. Okay, so then lambda plus is going to get moved. The power 2 to the lambda plus is going to move to gamma plus, which is above lambda. So lambda is no longer a strong limit. Okay, so E does preserve, but so E destroyed all the strong limits that are not limit points of C. So all those lambdas like that I just showed you, if that lambda was alpha inaccessible, it's not even a strong limit anymore, so it can't be alpha inaccessible. Okay, so let's go to the last slide. Okay, so we see this guy, and he's having a crisis, and like maybe it's like a philosophical crisis, and he's like, wait a minute, I did all this stuff, I've been through all these universes, and did I destroy too much? Like, he's worried that maybe there aren't even any inaccessible cardinals left. Okay, well, guess what? Everything's fine. Everything's totally fine. Let's just see what happened. We started in V. Kappa is alpha plus 1 inaccessible. We arranged the continuum so that 2 to the aleph sub n, the power set of, so 2 to the aleph sub n is aleph sub n plus 1. It's very nice. Nothing, don't worry, nothing got destroyed there. And then in the next step, we ride this blue star, and now we're riding this green star, and this green star is just adding a club. Now the great thing about the club that I don't even know if I mentioned, that the club has unbounded, through a density argument, we can see that this club contains unboundedly many beta inaccessible cardinals for beta less than alpha. Okay, so yes, so we take this pink star. Now this pink star is possibly, it isn't preserving all inaccessible cardinals. It's destroying all strong limits that are not limit points of C. But the great thing is C has unboundedly many beta inaccessibles for beta less than alpha. So therefore, kappa can still be alpha inaccessible because it has unboundedly many beta inaccessibles below it for beta less than alpha. So it is alpha inaccessible. Okay, so we're good. It's not alpha plus 1 inaccessible because E destroyed all the strong limits that are not limit points of C, and C doesn't have any alpha inaccessible cardinals. Okay, so we're fine. We destroyed exactly what we wanted. We're still in a model of ZFC, thank goodness. And now we've just got that kappa is exactly alpha inaccessible. Okay, so we made it through. Okay, thanks for coming with me on that journey, you guys. I was like a little worried, am I gonna be able to get this all out? Okay, I will say the measurable case, which maybe I'll do tomorrow. I'm hoping, what I'd like to do is the measurable like action scene tomorrow, and then next week we can just get it all into the degrees of supercompact cardinals and the forcing, which is the main part. Now, these forcings to, I mean, the forcings to do this, the next part, and then like we have these like representing functions and stuff. We do hit some roadblocks in the degrees of supercompact cardinals, just like we sort of kind of hit some roadblocks with the inaccessible and Malo. So but the main part of the talk really is about the introducing the degrees of supercompact cardinals, and like the forcing, we'll have fun with it. I won't get too bogged down with it because it's only 20-minute talk. So this little thing I just did right now is only going to be like 2 minutes. So, okay. Well, anyway, thanks for coming. You guys, I love hanging out with you guys and talking to you. So, so I'll see you tomorrow, and I hope you're having a great day and a great week. And it's getting so nice. Like, it's very nice out. Like, all the snow is melted off my car. It's like, I think I'm going to go for a walk. Okay, so I'll see you later.